gigantic, incredible, amazing, and stupendous. You have to see them to believe them, and even then, you might not. Now, more of the world's biggest machines on Modern Marvels. Welcome to the world of extreme machines. Those giants who lay claim to being the biggest, longest, heaviest, and most powerful on Earth. Supersized monsters that can literally move mountains.
When I say it's beyond imagination, it is beyond imagination.
Big brutes that boggle the mind.
The typical reaction is, oh my gosh, I never knew how big it was.
Miracle machines that can take your breath away.
When we say it's the biggest big screen on the planet, there's just nothing like it anywhere in the world.
Giants that can do the impossible.
We could suck all the air out of Madison Square Garden in about 2 minutes.
These are machines like no other. These are the world's biggest machines. And many of them are built to fly. Ever since the Wright brothers took flight in the first successful airplane in 1903, we've been on a never-ending quest to thrust more payload into the sky. From Howard Hughes' Spruce Goose flying boat to the ever-dependable B-52 bomber, up to today's airline workhorse, the Boeing 747. We've been driven to build them big. And no one more so than the Russians. The Antonov 225 is the world's largest airplane. Its dimensions are staggering. It's nearly a football field in length from nose to tail, and its wingspan stretches an amazing 291 feet. Built originally by the Soviets in 1988 to transport their prototype space shuttle, it's used today as a super cargo carrier, capable of carrying twice the payload of a Boeing 747.
Any of the numbers you use to describe the AN-225 come under the heading of superlatives. For instance, it was the first aircraft to fly that took off at a gross weight of greater than 1 million pounds.
Everything about this jumbo jet is massive. It's powered by 6 giant turbofan jets, each capable of pumping out 51,590 pounds of thrust. The Soviets had to incorporate many innovations into its design because of its size, including a 32-wheel steerable landing gear.
In addition to the nose wheel section being maneuverable, the rear parts of the main landing gear are also steerable. The main landing gear consists of, on each side, 7 units of twin wheel assemblies. The last 4 on each side are steerable. And having the last 4 trucks, as we call them, of the main landing gear assembly steerable on the aircraft makes it able to be turned in a relatively small turning radius so that you don't have to build massively large taxiways and parking aprons for this very large aircraft.
The Giant also sports a wide split tail, designed to avoid the air turbulence created by large piggyback loads, like the Space Shuttle.
If you have a single-tail aircraft, there's some turbulence that is set up by the airflow around your cargo that you're carrying on the back of the aircraft by making a double tail where the 2 tail sections are outboard, then the turbulent airflow goes between them. Then that allows for a smooth aerodynamic flow over the vertical fin and rudder assemblies on either side of the horizontal stabilizer.
The AN-225 made its international debut in a style befitting its dimensions when it landed at the 1989 Paris Air Show with a Soviet space shuttle on its back. beginning, it caused a sensation. However, its glory days were short-lived. After the fall of the Soviet Union in 1991, the plane was without a mission. It was grounded in Kiev and scavenged for parts. Then, after nearly 6 years, the only AN-225 ever built was rescued from the scrap heap by the Antonov Group, who put $20 million into refurbishing it as a cargo carrier. Today, their investment is paying off. Carrying everything from heavy construction machinery to oil drilling equipment to fleets of cars, the future once again looks bright for this giant of the skies. Crucial to the success of the Antonov and other big powerful planes was the development of the jet engine. Today, the engines are becoming giants themselves. Dr. Hans von Ohain of Germany and Sir Frank Whittle of Great Britain are recognized as co-inventors of the jet engine. Ironically, they researched separately from each other during the 1930s and knew nothing of each other's concepts. Yet both produced functional jet planes by the early 1940s. Jet engines operate by sucking in air with a fan. They then compress the air inside the engine and spray it with fuel, which is ignited. The burning gas expands and blasts out the back of the engine, thrusting the aircraft forward. General Electric has produced the world's largest and most powerful jet engine, the GE90-115B.
We've broken the world's record twice for demonstrated thrust, most recently demonstrating 127,900 pounds of thrust. That's equivalent to over 100,000 horsepower.
The massive engine was developed to power twin-engine airliners like the new Boeing 777. Many experts believe twin-engine aircraft may prove to be the wave of the future in the airline business, because they're less expensive to operate than four-engine planes. Even veterans of the aviation business are amazed by the engine's size.
They're pretty much awestruck. A lot of them really just are kind of silent and just, big eyes, and this look on their face is just almost incredible to see. It's so much larger than any other engine they've ever seen before.
Key to the success of the engine is its giant 128-inch diameter fan, one of the largest ever constructed for a jet engine. The fan sucks in enormous amounts of air that allow the engine to generate its record-breaking thrust. Most jet engine fan blades are made of extremely strong titanium. However, constructing a fan this large, entirely of titanium, would have made the engine impossibly heavy. General Electric solved this problem by designing new fan blades made of lighter carbon fiber polymeric materials, and then giving them a titanium leading edge for strength. The shape of the fan blades is also a key ingredient in creating the engine's enormous power. Older engines used simple straight up and down fan blades, but the GE90 is equipped with aerodynamic swept wing blades.
The unique shape of the fan blade is key to the technology of the engine as well, and that 3D shape, that beautiful 3D shape that you see, draws in more air than just a straight up and down or radial blade. It actually draws in more air in the same circumference, and that extra air gives us that extra little bit of thrust that we need.
Before the engine could be certified for flight, it had to be put through a battery of demanding tests.
The testing is to assure that the engine can fly in any environment safely. We look at any extreme environments and make the testing more severe than what you'll see in operation on an aircraft. We have water ingestion testing. We take in about 4.5 tons of water a minute and show that the engine can continue to operate and not stall, taking in that kind of volume of water. We also do hail ingestion testing. We have several little cannons that shoot hail into the engine. They shoot about 3/4 of a ton of hail in 30 seconds.
Nothing was left to chance. Technicians tried to recreate and analyze every possible problem that could happen to the engine.
An engine, when it's operating on an aircraft, takes in a lot of air. It can also take in anything else in the environment, such as a bird. So we're required per the FAA to shoot bird carcasses into the engine and to show that we can continue to sustain operation even after taking in the bird carcasses.
Perhaps the most important test of the engine is the flight test. Since the early days of aviation, special planes have been designated for testing new equipment.
GE actually owns a flying test bed, a 747 aircraft, where we test engines prior to doing flight test on any new aircraft. In the case of the GE 9115B, we had this huge GE 90 engine on the aircraft with 3 smaller engines.
Amazingly, the engine proved powerful enough to fly a giant 747 by itself.
We had these 3 smaller engines that we actually cut the power to all those engines and just flew it on the one GE 9115B engine. Another story about the flying test bed that's pretty amazing is the air that's pulled through the engine to generate the thrust. As it was exiting the engine, it was actually moving 400-pound rocks that were kind of rolling behind the engine. I don't think anybody expected to see that.
After 2 years in development, the $21 million engine is now a fixture on the Boeing 777, ushering in a new era for twin-engine airliners. Fixed-wing aircraft builders aren't the only ones who think big. The Sikorsky CH-53E Super Stallion is the largest helicopter in the Western world.
It's the largest helicopter that we own. The dimensions of the helicopter, it's 99 feet long. The rotor head is 79 feet in diameter. From the ground to the top of the tallest tailblade is going to be about 28 feet.
Ever since the 1950s, helicopters have been used to carry heavy objects slung beneath their fuselages on cables. Today, when it comes to heavy lifting on the battlefield, the CH-53E is the first choice of the United States Marines.
The CH-53 Echo was originally designed to carry 32,000 pounds at 100 knots indicated airspeed for 100 nautical miles, hover on station for 5 minutes, and then make the return flight home.
The technological wonder of the giant copter is its 79-foot diameter rotor assembly.
Most normal helicopters in the inventory today carry 4 or 5 main rotor blades. Ours carries 7, which helps provide that additional lift due to our size and capabilities.
The tail rotor is also of Goliath proportions.
Here, we're looking at the tail rotor of the CH-53 Echo. You can see it's extremely large, over 20 foot in diameter, and has 4 blades. It's larger than the main rotor head of most helicopters today.
The helicopter is capable of lifting heavy objects like these 2 Humvees with ease. The total combined weight of the 2 vehicles is over 12,000 pounds. During the maneuver, the copter's rotor blades subject the Marines on the ground to hurricane-force winds.
And what we'll do today is we'll approach the Humvees and hover over them, while our crew chiefs in the back help align the pilots over the load. We'll have a helicopter support team, approximately 6 Marines underneath our helicopter, and they'll hook up the external load to the helicopter. Once we pick the Humvees up off the ground, our crew chiefs will make sure the load is steady and is riding in the correct fashion, and they'll clear the pilots for forward flight.
This giant may be the Marines' heavy lifter, but in the long history of brute strength on rails, it's muscle machines like Union Pacific's 4000 series of steam locomotives and today's AC 6000 diesels that get the job done. In June of 2004, the Antonov 225 set a new commercial payload record by carrying 247 metric tons of construction equipment from Prague, Czech Republic to Tashkent, Uzbekistan. More of the world's biggest machines will return on Modern Marvels. We now return to more of the world's biggest machines on Modern Marvels. Today's giant locomotives are the latest muscle machines to power the railroad industry. When British engineer Richard Trevithick built the first practical steam locomotive in 1804, he started the industry on a fast track to building them bigger and bigger. During the steam era, this drive toward mammoth engines reached its zenith with Union Pacific's Big Boy 4000 series, the largest steam locomotives ever built.
Oh, the Big Boy was 132 feet 9 inches from coupler to coupler. It's about 16 feet 2 inches tall, about 10 feet, close to 11 feet wide. It weighed 1.2 million pounds, which is 600 tons when it was fully loaded with coal and water ready for the road.
First put in operation in 1941, the Big Boys were built to pull heavy freight trains through the steep mountain passes of the Rockies. Whenever they pulled into town, they drew an admiring crowd.
The ground would literally shake when a Big Boy rolled by, so they were very impressive machines to watch.
Designed and constructed by the American Locomotive Company of Schenectady, New York, the Big Boy presented its builders with some major engineering challenges. Because of its enormous proposed length, with 16 wheels attached to a rigid frame, it would be impossible for it to stay on track while navigating sharp corners. It just wouldn't be flexible enough. To solve this problem, it was decided to make the locomotive articulated, meaning it would have two engines connected by a hinge pin between them. Both engines would be served by a single boiler. When negotiating a curve, the front engine would be able to swing out freely around the curve, and then the back engine would follow. Supplying fuel to the giant locomotive also posed a problem.
The tender of the Big Boy was designed to hold 28 tons of coal and 24,000 gallons of water, and obviously a locomotive that big burned an enormous amount of coal and water in a trip up the mountains pulling a heavy train. Typically it would burn about 8 to 10 tons of coal in an hour and go through about 8 to 10,000 gallons of water in an hour. Shoveling 8 to 10 tons of coal an hour was more than any human could do, so there's a mechanical stoker in the engine. It's actually an Archimedes screw, and the screw is driven by a little small two-cylinder steam engine that sits in the tender, and the fireman controls the speed of that screw, and that pushes the coal into the firebox.
The firebox itself was of epic proportions.
Well, the firebox was one of the biggest ever put on a steam locomotive, which is fitting for a locomotive the size of the Big Boy. It's about 20 feet long, about 8 feet wide inside. There was literally an inferno inside a Big Boy firebox.
Built at a cost of $265,000 in 1941, which would be $5 million today, the giant engine delivered all the power its designers had promised.
The Big Boy produced in excess of 6,000 horsepower, and this was an exceptional amount of horsepower for the time, particularly for a steam engine.
It also delivered speed that would be impressive even today.
The speed of this locomotive was governed by the amount of tonnage that was tied onto the back end, but it could do in excess of 80 miles an hour.
Yet for all its power, by 1960, the age of the steam locomotive had come to an end, and even the incredible Big Boy was forced into retirement.
Well, steam engines were phased out really because better, more efficient technology came along. And the diesel engine is better economically, and it was a lot easier to maintain.
And today, there's a massive diesel locomotive that surpasses even the Big Boy. It's General Electric's AC6000.
The AC6000 behind me is one of the largest locomotives on the rails today. It's 76 feet long, it's 16 feet high, and it's 10.5 feet wide. The locomotive with a full load of fuel weighs 425,000 pounds or 212 tons.
This $2 million giant is quantum leaps ahead of the Big Boy in terms of technology.
The AC6000 is powered by one large 16-cylinder diesel engine. The diesel engine produces 6,000 horsepower for traction. That's power that goes down to the rails.
Everything about the engine is huge.
To put things in perspective, I've got two different pistons for you to look at. This is a piston out of a modern Class 8 over-the-road truck engine, the kind you'd see racing down the interstate highway. This piston will produce 112 horsepower in that engine. By comparison, this is a piston out of the GE AC6000 engine. This piston in that engine will produce 375 horsepower.
Although called a diesel locomotive, the engine is really a combination of power plants.
Most people don't understand that a diesel locomotive is actually a diesel-electric locomotive. The diesel engine produces horsepower, and it drives an alternator which produces electrical energy. That electrical energy is then controlled and fed down to 6 traction motors, one on each axle, and that's where the pulling power actually is produced.
The locomotive uses AC, or alternating current traction motors, which are very efficient and reduce wheel slippage significantly. In the world of railroading, wheel slippage is to be avoided because it reduces speed and power. By using separate AC motors on each axle of the locomotive and monitoring them through a central control computer system, the designers have ingeniously and significantly improved the train's traction, a key ingredient to the rail giant's success.
So each of the 6 axles on the AC6000 is controlled individually from the other 5. In that manner, when one wheel has a tendency to slip, it can be controlled and the other 5 axles can pick up some of the load temporarily until the locomotive passes across that slippery section of track.
There are only 106 of these Titans operating around the world today. They are the locomotives that are called in when only the biggest and the strongest can get the job done. On the water, the biggest and strongest of ships are specialty ships, giants that are rewriting the record books for size and innovation. Big boy steam locomotives were generating in excess of 6,000 horsepower in 1941. It wasn't until 1969 that a diesel-electric locomotive was built that could produce more than 6,000 horsepower. The Union Pacific DD-A40X Centennial. More of the world's biggest machines will return on Modern Marvels. Over 2/3 of the Earth's surface is covered with water. The monarchs of this aquatic domain are giant ships. They come in all shapes and sizes, and all have specialized tasks. From military giants, to cruise ships, to oil tankers, and huge cargo carriers. The world of big machines on the high seas is one of great diversity. Some of the largest and most impressive of these marine engineering wonders are the heavy lift ships. When it comes to piggybacking huge cargoes on the world's oceans, shipping companies, oil drillers, and the United States Navy turn to these giants of the seas, including Dockwise Shipping's massive Blue Marlin.
The Blue Marlin is indeed the largest heavy lift ship in the world by a considerable margin. She's 737 feet long overall and 206 feet wide.
The ingenious process by which heavy objects are loaded onto the huge ship is one of the marvels of modern naval engineering. Here, the Blue Marlin prepares to transport the massive Thunder Horse oil drilling and production platform from Korea to the Gulf of Mexico.
The Thunder Horse is definitely the largest oil and gas floating offshore platform ever built. It will weigh, at the time we transport it, some 60,000 metric tons.
Key to the loading process is the ship's ability to partially self-submerge.
It takes about 4 hours to fully submerge the deck of the ship by adding ballast water to ballast tanks within the ship to safely submerge it. And you'll note on the aft end of the vessel are 2 large, what we call buoyancy towers. These towers also contain ballast tanks, which we will fill with water, which enable the ship to submerge on an even keel.
Maneuvering the giant oil platform into place is a delicate operation, even though it involves thousands of tons of equipment and thousands of horsepower.
And using tugboats, the floating cargo is brought over the deck of our ship, whereupon we attach winch wires to the cargo from winch towers on the vessel. We then slowly bring the cargo over the deck of the ship into precisely the right position.
The final part of the operation comes when the Blue Marlin is resurfaced to a proper draft. Perhaps the Blue Marlin's greatest moment of glory came when she was chosen to ferry the stricken Navy destroyer USS Cole back to the United States after it was attacked by terrorists in Yemen in October of 2000.
The hole in the side of the Cole was very big and made the vessel unseaworthy. So basically the challenge in loading the USS Cole was not so much the weight of the ship, because a destroyer like that weighs about 8,500 tons, which for the Blue Marlin is a relatively insignificant amount of weight. The challenge really was more, how do you put a long, narrow body like the Cole onto the top of our ship and stabilize it so that it doesn't tip over. The transport of the Cole was very smooth, very uneventful voyage, very successful, I would say, on the part of Dockwise and the U.S. Navy.
Another class of ocean giant that boggles the mind is that of oil drill ships. The biggest of them is Transocean's Discoverer Enterprise.
The ship's 835 feet long, 125 feet wide. The derrick tower is more than 375 feet over the surface of the water above the ridge.
Drill ships ply the oceans, exploring their depths for oil and gas fields. As oil reserves dwindle onshore and along coastlines, oil companies are turning more and more to deep-sea exploration.
The need for additional reserves in oil and gas production has driven the industry into ultra-deep water. In order to satisfy our clients and reach these new frontiers, we have to continue to develop bigger and better tools.
The Discoverer Enterprise's hull was built at the Estano shipyard in El Ferrol, Spain. She was completed in Pascagoula, Mississippi in 1999. The ship isn't just big, she's revolutionary.
We decided to throw out all the conventional thinking and start all over with a clean sheet of paper. Part of that process led to the development of what we call dual activity drilling, where we utilize two complete sets of equipment on one rig to be able to drill two wells simultaneously. The ship is so big because it has to accommodate two complete sets of drilling equipment.
This dual drilling capability allows the Discoverer Enterprise's clients to save up to 40% developing oil fields because it speeds up the whole process. The ship often operates in such deep water that anchoring while drilling is impractical. Instead, an ingenious high-tech stabilizing system has been developed.
So we use what's called dynamic positioning. Dynamic positioning consists of computer-controlled thrusters that have inputs from satellites for positioning. We take inputs from satellites to determine what our position is. We then use a computer to very tightly control the position of the vessel using 7,000 horsepower thrusters.
The system is so efficient that it can hold the ship steady in gales up to 70 miles per hour.
In very high winds, in fact, we're able to maintain location within a few tens of feet in thousands and thousands of feet of water.
All of this combined technology adds up to a truly amazing ship. One that is capable of digging to incredible depths.
The ship is capable of drilling in 10,000 feet of water or more. In addition, even in that water depth, we can drill wells that are nearly 5 miles deep below the seafloor.
Oil drill ships may be the champs for digging deep into the earth beneath the sea. But when it comes to digging on land, nothing can top the giant excavators. The engines aboard the Discoverer Enterprise can generate enough power to serve approximately 40,000 homes. More of the world's biggest machines will return on Modern Marvels. When it comes to super-sized machines, giant earth movers are at the starting point of our world economy.
Without them, it just would not function. All raw materials have to be mined to produce the cars we drive, the streets we drive on, the buildings we work in.
Among the biggest of all earth movers are giant bucket wheel excavators. Some reaching over 700 feet in length, 300 feet in height, and weighing as much as 30 million pounds. They're the largest machines on land capable of moving under their own power. Bucket wheel excavators, or BWEs, are used primarily to mine lignite, or brown coal.
It works best in loose, sandy material. The digging wheel and its multi-buckets is not designed for digging through solid rock or glacier-type boulders. It needs looser, more gravelly-type material to dig through efficiently.
This giant erector set of a machine is made up of many components.
You have the large digging wheel at the front, which is 71 feet in diameter. It is connected to a large boom, which then connects to the central tower. The central tower has a conveyor bridge, which extends from the back end of that, and then that is hooked to what is referred to as a discharge unit. The discharge unit carries the material onto large overland conveyors.
Although incredibly efficient as earth movers, BWEs pose no threat to the world's land speed record.
The speed of these machines are up to perhaps maybe about 30 feet per minute, which would translate into about 1/3 of a mile per hour.
However, the fact that they can move at all is a technological miracle brought about through the use of giant crawlers.
The main tower assembly is supported by an undercarriage with 12 massive crawlers, each 49 feet in length. The reason that these bucket wheel excavators like 293 require so many crawlers is for flotation. Because of the underfooting that the machine works on, it has to be extremely level, extremely stable.
Computers allow the operators to monitor all aspects of the digging operation. But even with this technology, several crew members are needed to operate the machine.
These machines typically run by about 4 or 5 people. There is one operator that is located in the main operator's cab. This operator would have an overall control of the whole machine.
The price tag for one of these brutes is as big as the machine itself.
The bucket wheel excavator of this size cost over $100 million. The weight of the machine, obviously a major factor in determining the cost of the machine, and the sophistication of the equipment.
Yet if you want to move an astonishing 314,000 cubic yards of material in one day, a giant bucket wheel excavator is the only way to go. Another Goliath amongst earth-moving machines is the Terex O&K RH400 hydraulic front shovel excavator.
The RH400 is the world's largest front shovel. 57 cubic yard bucket, 4,400 horsepower, 1,100 tons operating weight. It is simply huge. There has never been another hydraulic excavator like the RH400. Everything kind of looks like it's out of a science fiction novel or something.
With its gigantic bucket, it's able to do the work of many smaller excavators in less time, and with more efficiency.
The RH400's large bucket is capable of loading a 240-ton capacity truck, 3 quick passes, with each pass averaging less than 29 seconds.
One of the main advantages of a hydraulic diesel shovel is its mobility. Unlike some electric shovels tethered to power lines, it can move freely.
Once it's finished working at a location, it can relatively quickly move to another working location and go right to work.
Mining companies thinking of buying the giant shovel can also expect to shovel out a lot of cash.
they have to be ready to write a big check for, in the neighborhood of $10 to $11 million. But because of their size and their massive capacities, their productivity should outweigh the cost of the machine in the long run.
And speaking of long runs, in the world of publishing, huge new printing presses are bringing a whole new meaning to the words, power of the press. Except for maintenance days, bucket wheel excavators work 7 days a week, 24 hours a day, 365 days a year. More of the world's biggest machines will return on Modern Marvels. Possibly more than any other invention, the printing press changed the world. And now, they're among the world's biggest machines. Prior to the invention of the press, written information was available only to an elite few who read books that had been written by hand. Johannes Gutenberg developed the first press with movable type in Germany around 1440. After its invention, knowledge about science, literature, technology, and journalism became available to everyone and spread across the globe. Today's presses are giant machines, often housed in buildings acres in size, and capable of printing billions of pages per week. The new $72 million press system for the Indianapolis Star newspaper is one of the most advanced in the country.
This is one of the largest press systems in the world. It stretches almost 400 feet in length and is 65 feet high. It's made up of 24 towers and 4 locations with folders. It can actually be run as 4 individual presses, or it can be run as a series of presses connected, and that's the reason it's all in one long line.
The first step in putting news to print comes when stories are electronically transmitted to the press site from the Star's downtown Indianapolis newsroom.
Once that page is transmitted out here, we output the page through a film processor that provides us with a large, full-size page negative that we then take and move over to our plate-making machines. The plate-making machines then have light that exposes the negative onto the plate, and the plate then has the finished image that we want to reproduce. The plate is then moved out into the press room and put on the cylinders of the press in preparation for printing the product.
Next, a web of newsprint is threaded through the press in preparation for the printing process. Then the giant machine is brought to life with the push of a button. The entire system is completely computerized.
Everything on the press can be controlled from this location. As the web passes through the press, there are sensors that tell us what the tension is of the paper. The better the tension and the more accurate we run the tension, the better the reproduction as the paper goes through the press.
Feeding this giant beast with newsprint is a never-ending task.
This is our newsprint supply warehouse. We have a 25-day supply of newspaper in this warehouse. Each one of the rolls will unwind to about 11.5 miles worth of newsprint.
Deep in the bowels of the press building, a complex automated system has been built to get the giant newsprint rolls to the press as quickly and safely as possible. The awesome machine's demand for ink is also insatiable.
This is our ink tank farm. We've got 6 large tanks here, 2 7,500-gallon black tanks, and 4 2,500-gallon tanks that we use for our blue, red, yellow, and spot red colors. During the course of the year, we'll use over 200,000 gallons of ink.
One unexpected byproduct that resulted from the installation of the new presses was the amount of climbing workers had to do to maintain them.
I would say that overall our operators consistently lost a few pounds each moving to working on these presses because of the size of them.
Papers rumble through the press at up to 25 miles per hour. Yet it's so well engineered that vibration is minimal.
We can take a penny and balance a penny on edge on the side frame of the press when it's running 75,000 an hour, and it will stay standing up for as long as you leave it there.
After the papers are printed, they're automatically sent to the packaging department.
Now the gripper conveyor is like a series of hands that have fingers on it that pick up each paper individually and then take those papers to our mailroom department or our packaging department. In our packaging department, we would take those papers, we'd drop them off and put them into another in-feed conveyor where they go into a stacker where stacks of newspapers are created. We put a tie around those papers, then they get sent out to our distribution centers.
With a possible combined output of 300,000 copies per hour, this giant printing press system adds some real mass to the notion of communication. Of course, another media titan is the television. From the days when screens were only inches wide to today's mammoth screens, it's a technological wonder. Giant LED or light-emitting diode screens have become fixtures throughout the world. The largest continuous LED screen in the world is located at the capital of all things extreme and extravagant, Las Vegas, Nevada. By day, thousands of tourists pass right under it. Many of them unaware that this giant canopy covering the city's Fremont Street transforms into one of the wonders of the electronic age by night. It's called Viva Vision, and it's the star attraction of the Fremont Street experience in downtown Las Vegas.
It's close to 5 football fields long. It's 1,500 feet in length. It's 90 feet up in the sky. There's over 12 million lights on the canopy. It's supported by 550,000 watts of sound. So when we say it's the biggest big screen on the planet, there's just nothing like it anywhere in the world.
At the heart of the gigantic display are the tiny LED lamps.
LED is an acronym for light-emitting diode. A light-emitting diode more or less houses a microchip, in a sense, inside a lens.
Through the wizardry of Viva Vision, millions of the LEDs are orchestrated, using the mechanics of television to create the giant screen and its colorful display.
This is our red LED, and this is our green, and this is our blue. When we bring all 3 colors to full, that gives us a white pixel. Now here we have the LEDs on at full power. When we're using them in functional display with Viva Vision, we mix and match voltages. Each one of these LEDs has 256 levels of dimming capability, thus giving us our 16.7 million color combinations.
The whole project emanates from a master control room located high above Fremont Street. All aspects of Viva Vision are controlled by a massive bank of computers.
Viva Vision works with an array of 8 computers that power each section of the canopy itself. So within those 8 computers are a number of hard drives and lots of storage to accommodate these large show files.
The $17 million Viva Vision screen programs everything from animation to live action to music videos and special events. What was conceived as a dream screen has become a reality and a resounding hit. In this town of instant winners and losers, the Fremont Street Experience Viva Vision screen is clearly a winner. And it takes its special place amongst the giants we call the world's biggest machines.
Next on History, the mid-'80s saw a serious lack of
Muscle car fever in America.
So Buick came out with this mean-looking beauty. Two teams muscle their way under the hood and settle on the racetrack.
It was mean in '85 and it's still mean today.
1985 Buick Grand National. Next on the History Channel.